Hello there, welcome to section 2, that's refraction at plane surfaces. Let's look at the objectives. The first objective is to describe the concept of refraction and state the laws of refraction. Secondly, explain how refraction takes place from one medium to the other. Explain the meaning of the refractive index. Able to state what the Snell's law of refraction. Explain the phenomenon of total internal reflection and the occurrence of the critical angle, which is very important. State the relationship between refractive index and wavelength of light in two media. And lastly, state some applications of total internal reflection. Now, let us consider two media. With the reflection, we are considering only one media. I'll use this schematic diagram to explain to you. So when you say refraction, what is refraction? Refraction is when light travels from one medium to the other medium, and as a result, light rays tend to what? To bend. And it's always bend whether towards the normal or away from the normal. With this schematic diagram, you can see that we have one medium here, we have a second medium here. Our first medium here is what? Is air. And the second medium here is water. And we have our normal here, which is perpendicular to this surface, that is 90 degrees. And we have our incident ray here, and our angle of incidence to the normal here. We also have a refracted ray, that is the R, and it's the angle of refraction is to the normal here. And in refraction, anytime light rays travel from a less dense medium, when we are comparing these two media, air is very less than that of water. Anytime a light rays travel from a less dense medium to a more dense medium, the refracted ray tends to bend towards what? The normal. Should in case we have a light ray that is this time around traveling from, you see the arrow here, travel from a denser medium to a less dense medium, you see that the refracted ray will bend away from the normal. And when we talk about the speed, look at this diagram here. The speed of light in a dense medium as compared to a less dense medium, it's always slow. So here, suppose we have a vacuum or air, and the light rays travels here. We enter into a glass prism, or let's say water, the speed will tend to be lesser, and it will get speed up again when it moves out again. One very common example that we can see in our house or experiment in our homes is when we put a pencil in a glass of water. You can see that there's a bend here or there's a shift when you slightly look at the side of it. And for the laws that we have in refraction, that's Snell's law, we can state that the incident ray, the refracted ray, and the normal at the point of incidence all lies on the same plane. And also, the ratio of the sine of the angle of incidence, that's I, to the sine of the angle of refraction, that's R, is a constant. And mathematically, we can express the second law as N1 sine theta 1 equals N2 sine theta 2, where N1 here is the refractive index of our first medium, and the theta 1 is the angle of incidence, whilst the N2 here is the refractive index of the second medium, and the theta 2 is our angle of refraction. And the next slide, I'll be explaining to you how we can calculate for the refractive index. of some medium. In refraction, there are some key formulas that we need to note. And the first one is N equals C over V. Actually, this formula here is the same as what we have here. We have another formula too here, that is N equals the wavelength of light in air and also the wavelength of light in the material. There's a deduction for this and it's in our model. Let's go back to this formula where we have N to be equal to our C over V. The C here is the speed of light in a vacuum, which we know to be 3 times 10 to the power 8 meter per second. And the V here is the speed of light of the material to be calculated for. Or let's say is the refractive index that you want to rather calculate. So supposing that we have a material like this, a glass block, or let's say we have water, right? And this is our normal. It's supposed to be straight. And light rays enter into this material from air. And we want to find the refractive index of this particular water. Or better still, we want to find the speed of light in this particular water. Already you know that the speed of light is what? 3 times 10 to the power 8. So this is what it's left to be calculated for, the V. We know that N, that is the refractive index of water, is already what? 1.33, which I think you'll be given, or there are some things that you already have to know and you can Google it and find out. So we have 1.33 here. You have C to be 3 times 10 raised to the power 8 here. You just make V here the subject, then you find the speed of light in this water. It can be a glass block, it can be any medium at all. The same way you can also find the wavelength. Whether the light source that you are given is a longer wavelength, shorter wavelength, any type of wavelength, you can use it to find even the type of light that you are being given. So when you are given a question like this, you will either be given the refractive index for you to find or the wavelength of the medium to be found. The wavelength of light in the medium to be found. And it shouldn't be a headache. There are more examples in the models that you can try your hands on. Let's look at a phenomenon called the total internal reflection. This phenomenon is a very interesting phenomenon and it has so many applications in this world. What is total internal reflection? The complete reflection of light rays reaching an interface with a less dense medium when the angle of incidence exceeds the critical angle. So let me use this schematic diagram to explain to you. We have 3 diagrams here. We have a denser medium to a less dense medium. We have A traveling to C, that is from a denser medium to a less dense medium. And we have A traveling to B, but this time around it's reflected. So let's look here. Because we are traveling from a denser medium to a less dense medium, automatically we expect that the angle of refraction should bend away from the normal. But in case we're able to move this particular angle here to increase a little bit, let's move here. It's moved a little bit. Because we've moved it a little bit, this angle here right now becomes straight on the what? On the Y. And right now the angle of refraction becomes what? Becomes 90. But all this while we have to take note that there is a partial reflection that is what's going on, and that is the what? The B. So this particular schematic diagram explains the critical angle actually. So that when we exceed an angle where we have the angle of refraction to be 90, we're saying the incident angle right now is called what? The critical angle. Let's look at our third schematic diagram. Should in case we exceed the critical angle, that is where we experience what? Total internal reflection. So the angle here right now is increased. And we have a very total internal reflection. This time around, it's not partial as compared to the previous schematic diagrams here. And we're going to have a total internal reflection. And there's one popular formula here that explains it. And this formula here is derived from the Snell's law. I hope you remember, where we have our N1 sine theta 1 equals N2 sine theta 2. And I'll give this one to you as an assignment to go and find out how you can deduce this formula to get this. Let's look at the applications of total internal reflection. And one common one is it is used in many application optical instruments like the binoculars. So in the binoculars, they have some particular prisms called the probe prisms inside, where total internal reflection occurs inside before it's being magnified. Another application too is the principle behind the optical fibers in telecommunications. So you see, we can send information through a fiber from here to all over the world through our internet cable that we use, and it's very fast. And because light travels 3 times 10 raised to the power 8, it can send information very fast. And this application is due to what? Total internal reflection. In the practical section of this, I'll be showing you some interesting experiments that we've done in the lab, where we use a laser to pass through some fibers, demi-fibers actually. The second application of total internal reflection is the submarines, where they use the periscope. Another one too is applied in cutting of diamonds, and the last one, the formation of mirages. And I hope you know what are mirages during sunny days.